My name is Santiago Blanco Canosa. I'm chairing the next session until before lunch. And our next speaker is Stephen Wilson from the University of California, Santa Barbara. And he's talking about correlations and topology in Kagome lattices. So, Stephen, thank you, please.
Great. Yeah, thank you very much for the introduction, Santi. And yeah, thanks to the organizers for the opportunity to come and give you guys a lecture, or two lectures, on what we think is an interesting field, which is electronic properties and symmetry breaking in Kagome lattices. And so just some background. So I'm in the materials department at the University of California, Santa Barbara, and I'm an experimentalist. So our group, we grow new materials and try and characterize them and understand what type of electronic ground states they have. And so that's by way of introduction, but it's also a bit of a warning or a disclaimer for what follows. You know, you have a lot of leading condensed matter theorists presenting some of these topics. I'm an experimentalist, so there's a real danger of damage to your minds in what follows. So just that's my warning. So I have two lectures, and so the first lecture is meant to be an hour of motivation or brainwashing for why we think that the Kagome lattice is a kind of uniquely interesting material platform or pattern within materials to try and stabilize interesting electronic states which have a flavor, a bit of what Alan started the day with in terms of non-trivial band topology, and then followed by non-trivial electron-electron interactions, which was the second lecture of today. Okay. So just an outline I'll be talking today is first I'll just give you an introduction to the Kagome lattice in general and just sort of a qualitative overview of why it's interesting to study. And then I'll just very briefly introduce the operative model for a lot of the motivation, which is the Kagome lattice Hubbard model. And then I'm going to talk about the Kagome lattice and phenomenology in that lattice in two limits. The first is, I guess, certainly the more experimentally tread pathway, which is the Kagome lattice insulators, which has been a topic of interest for a long number of years due to the strong geometric frustration in the magnetic sector of the system. And then the second part, we'll be talking about why we think Kagome metals are interesting, which has been of theoretical interest for a very long time, but it's only, say, in the past, 6 or 7 years, that there's been a lot of kind of experimental real materials manifestations of some of the effects that have been predicted. Okay, so. All right, got it. All right, so let me just talk about the Kagome lattice. So what is it? There we go. And so it was sort of dubbed, this pattern is the Kagome lattice, and it was dubbed so by original work by Hisumi and Suyozi, which they named this sort of network of corner-sharing triangles after this pattern of basket weaving, Japanese basket weaving. And they originally sort of started studying this as a statistical model for spin physics, following, for instance, Ansauger, Temperley, and Vanier. And their idea was to then take, I'm just going to use this, it was to take a honeycomb lattice and then just to decorate the midpoints along the honeycomb lattice and then connect those, and then you end up with this Kagome network. And they studied sort of the physics, the spin physics of that system. And so this is sort of the genesis of the name Kagome with this particular pattern in physics. And then if you look more broadly, so I mean, a few years ago in popular culture, there was this sort of so-called Einstein tiling, where this guy Smith came up with this, which is called this top hat model, that you could tile all two-dimensional space in this pattern that doesn't repeat. And so this sort of got me interested in sort of this 2D tiling field. And so if you just look at sort of tiling of two-dimensional space, it turns out that there's only 11 ways to do it with these Archimedean lattices, which are just tiling of regular polygons, and so vertices of the same type and sides, lengths of the same length. And so of these 11 types, the Kagome lattice is one of them, okay? So it's sort of a kind of fundamental texture that you should expect to see sort of in two-dimensional networks, especially if we're talking about high symmetry structures in nature. And again, it's a network of these corner-sharing triangles that I'll talk about a bit more. And if you think about Kagome lattices in nature then, right, okay, it's nice as a mathematical concept, but can we expect to find it in real materials? And the answer is yes. So this is one of the more appealing things, is that, you can find Kagome networks in many real materials. And so material scientists have known this for a long time, that if you just take some network of balls, okay, let's say small balls, and you look at hexagonal close-packed networks, and then you make 2/3 of the balls small versus a 1/3 large, okay, and then you look at what kind of structures that this wants to kind of breathe into, it turns out that the favored superlattice that forms is really to distort into a Kagome lattice stacked by a triangular lattice, and then basically the details on how you phase these stackings depend on the details of the material itself, but it basically shows that the Kagome network is actually something that's actually favored to form, even in this sort of very simple model of binary intermetallics, okay? And in fact, if you look at the sort of histogram of the number of known binary intermetallics, where you have some type of A-B site ordering, a lot of the most commonly formed variants, such as this sort of C15 Laves phase, which has host networks of Kagome connectivity. This is a three-dimensional material, but it just goes to show you that the Kagome networks themselves actually are reasonably commonly formed in nature. Okay. Okay, so why is the Kagome lattice interesting? So if one thinks about just hopping across a Kagome lattice, and you think about sort of this sort of tight binding model, the band structure that you get when looking in this sort of just a single orbital, so you get a three-band model, is the following. So you get a dispersion of the bands up to these Dirac points, these Dirac crossings that Alan talked about early in the morning. You get a series of two saddle points, and then you also get a flat band, okay? And I'll talk about these three features in the band structure individually, but just as a calibration for people who maybe haven't looked at the Brillouin zone for a Kagome lattice or hexagonal lattice, just some terminology. When I talk about the M point of the Brillouin zone, that's sort of the midpoint of the edge, okay? And if I talk about the K point, that's the corner, okay? And the gamma point is the center. And so basically one can do cuts along these high symmetry lines and kind of visualize these different features that come from this simple sort of tight binding model of the band structure of a single Kagome layer, okay? So again, you get sort of, at the K point, this Dirac crossing, okay, which can be gapped by spin-orbit coupling. And at the M points, you get a saddle point below the Dirac crossing and a saddle point above. And then at higher energies, you get this flat band. Okay, and so that's this is the sort of weakly interacting metallic or itinerant limit of the Kagome lattice. And then the other limit, as we can talk about, as we just heard in the previous lecture, is that if you push this system to half filling and then you start just cranking up correlations, eventually you'll gap out the charge sector and you'll undergo this Mott metal insulator transition, right? So sitting at half filling and turning up correlations, eventually the charge degree of freedom gets gapped out. You have upper and lower Hubbard bands, and then this system becomes a Mott insulator. And the operative regime for there, since you've removed the charge degree of freedom, you can think about systems in terms of a Heisenberg model. We can think about exchange between electrons in the magnetic sector, okay? And so these are the two limits that a lot of sort of the more interesting phenomenology of Kagome lattices have been discussed. Okay, so first I want to start off with Kagome lattice insulators, okay? So these are going to be regimes where, again, we're at half filling, and the Coulomb interaction is strong enough that you gap out the charge degree of freedom, so you have it's a Mott insulator with reasonably strong magnetic exchange J. All right. So the first bit is if, let's say that the magnetic exchange across the Kagome lattice is antiferromagnetic, okay, at the nearest neighbor level. And then that leads to what we call real space magnetic frustration of the antiferromagnetic bonds, okay? And so one way of visualizing that, this is sort of the canonical picture of thinking about a triangle. I have a three sublattice system. So now I can basically, if I have an antiferromagnetic interaction along each bond, then it's difficult to satisfy all three at the same time, right? And so then the system ends up being what we call magnetically frustrated. So it turns out, in the Heisenberg limit, nature kind of solves this problem by saying, okay, I'm going to have these three spins rotate 120 degrees from each other, and you end up with this sort of 120-degree rotated ground state, and its long-range magnetic order can form in this limit. Okay, so this is the known ground state of the Heisenberg triangular lattice model, but it turns out the Kagome lattice is maximally frustrated in this limit. Okay, and actually its ground state is still in the sort of the spin 1/2 limit, which is sort of maximally quantum. is still studied. Okay, and so there's predictions of that this ground state forms what's called a quantum spin liquid ground state, which I'll talk about more in a moment. But it's but basically the ground state of the Kagome lattice and the spin 1/2 limit is thought to host extensive degeneracy and unstable to sort of quantum fluctuations. And the quantum fluctuations in this language is just the uncertainty principle, right, for the spin, which is maximal in the spin 1/2 limit. Okay, so one way of thinking about this, like kind of qualitatively, is that if I go back to the sort of tiling example, you can think about which of these tiling patterns is sort of maximally frustrated in 2 dimensions, okay? And so some early work by Richter and Hove, just kind of thinking about classical spins, you can try and define sort of a misfit parameter from across all of these lattices, where you can just basically just try and tile them antiferromagnetically and sum over the energy of the satisfied bonds, and then look at the energy associated with the unsatisfied bonds. And then you can try and look at the ratio of the unsatisfied bonds over the sum of the two and define this sort of misfit parameter M. And so first off, okay, even-sided polygons in this tiling pattern, right? These are unfrustrated, okay? So you can ignore these. And then if you pick lattices with only equivalent bond types versus those with inequivalent, so we pick only the equivalent bond types, you're down to the Kagome lattice and the triangular lattice. And then if you were then to just basically, using this misfit parameter, you can calculate the energy of the classical Heisenberg antiferromagnet, look at the energy increase per bond due to the frustration. The triangular lattice and Kagome lattice sort of have the equivalent level of frustration, but sort of the law or the rule of thumb is that the strongest quantum fluctuations are expected to occur if you have this largest misfit parameter and the lowest coordination number per site, and then that would be the Kagome lattice. Okay, so that's at least one way to think about it qualitatively, in a very hand-wavy way, why the Kagome lattice is special amongst these sort of patterns of 2D tiling. Okay, and so indeed, if one looks at this sort of Heisenberg model, the J1, J2, J3, okay, so this is looking at the nearest neighbor exchange, so that's between the two spins here on a triangle, and then you can look at next nearest neighbor exchange, and you can look at third nearest neighbor exchange. You get actually a very complicated and rich magnetic phase diagram, okay, with a lot of non-trivial magnetic ground states. So this is some work from, I think, Donna Shen and Leon Balence's groups, where, again, there's a regime here in the ground state which is called the quantum spin liquid phase, which I'll talk about in a second, which is a very special magnetic ground state of the system, which is inherently dynamic. There's other regimes where, as you tune the ratio of these extended exchange couplings, where you can have valence bond crystals or so-called chiral spin liquid states, or even these sort of very complicated magnetic textures, which is this one's called cube octahedron 1. But you can see it's this very complicated non-coplanar magnetic ground state, which can give rise to a lot of unusual properties of the system. For instance, topological Hall effects and things like this can occur in magnetic ground states like this. Okay, but I would say historically the big driver in studying the magnetic ground states of Kagome lattices really has been searching for these different flavors of these so-called quantum spin liquids, which are predicted to form. And so what is the quantum spin liquid? So this is a term that was introduced by Anderson. So basically you can imagine the instability of the system is to form pairs of singlets across the triangles, okay? And if you think about the way of doing that, there's many different ways of tiling it. In fact, there's an extensive degeneracy of the way of forming these singlets. And so you can imagine the system sort of fluctuating between these different configurations. And this is sort of the definition of the so-called resonant valence bond state. And so what this ends up creating is what's a system which has a high degree of long-range entanglement of many spins that can occur in many different flavors depending on the details. Okay, so there's so-called gapless and gapped quantum spin liquids. So that has to do with whether or not there's an excitation gap into these sort of fluctuating states. And in many of them, there's sort of topological order and emergent quasi-particles that are predicted to occur. For instance, anyons are predicted to occur in 2 dimensions. And some of the fundamental excitations of these systems and sort of topologically non-trivial excitations, you can get sort of fractionalized quasi-particles. So you can have excitations that have, like the charge degree of freedom is gapped out, but you can have sort of spin 1/2 excitations with charge 0. And these can be created in pairs in these topological spin liquids. And I won't go through all of the details, but I just want to just highlight here, this is a very nice review by Lucille Savre and Leon Balence, which has this nice kind of categorization of the different flavors of spin liquids that are predicted to form. So just like there's many different flavors of superconductors, there's many different flavors of spin liquids, and in reality, actually experimentally determining which one you have is actually non-trivial. But here's just sort of a pattern of, a table with kind of different theoretical predictions for like measurable properties which might relate each flavor of a spin liquid to its categorization, to a material manifestation. Okay. All right, so that's sort of long been a pursuit in looking at Kagome lattice antiferromagnets, but also looking at unfrustrated magnetism Kagome lattice also has some interesting consequences, meaning one can look at the excitations of an ordered state across the Kagome network. In particular, let's say you have a ferromagnetically ordered state. This pattern of excitations can also have a topologically non-trivial character. And so one way to think about that is the magnons of the system. And so by magnon, I mean, here's just the sort of a nice cartoon picture, is that if you have a magnetic ground state, in this case a ferromagnetic exchange, then I can look at the sort of excitation of that by flipping a spin. So I can look at a spin 1 excitation across this ferromagnetic chain, and so that'll create a spin wave with some well-defined wavelength and energy. Okay, and so one can map the dispersion of this excitation of your magnetically ordered state, and this is the so-called magnon spectrum of the system. And you can do this in 2 dimensions, of course. In a 2-dimensional ferromagnetic state on a Kagome lattice, perhaps unsurprisingly, also kind of mirrors the magnon spectrum, mirrors the band structure in the electronic band structure. So you get Dirac crossings in the magnon spectrum, as well as a flat band feature at high energies. And so this flat band here actually turns out, basically, if you think about what this mode is an optical mode. And if you think about the spin rotation within this particular optical mode, the rotation from the phase of this spin rotation and this spin rotation propagating outside of this inner hexagon actually cancels. And so you end up with a dispersionless flat magnon mode. And so, as Alan mentioned, we'll talk about that more in the electronic sector. Okay, and we talk about flat bands in the electronic band structure. But these types of localized states also can occur in the magnon sector in the insulating state. And so what can happen then is this flat band can get gapped out if you apply an antisymmetric exchange interaction like Dylashensky-Maria interaction, which is basically, if I think about an exchange between 2 different spins, if the midpoint of that exchange is not a center of inversion for the crystal, then there's an exchange term that tells the spins that they don't want to be parallel to one another anymore. They want to actually be 90 degrees to each other. So depending on the mix between the Heisenberg and Dylashensky-Maria interaction term, you can end up with some canting. And so what that energy scale actually can also then act sort of like spin orbit coupling in an electronic band structure, and it can gap the flat band from these quadratic band touching points. And from that, you can actually get the so-called topological magnon insulator, where there's predictions of getting sort of magnon states which can propagate along the edge of the material. So it's just meant to give you a flavor that there's, even in the Kagome lattice insulators, there's sort of these predictions of sort of topologically non-trivial states, but in the magnetic sector. Okay, so just because I won't talk about these tomorrow when I talk about materials examples, I just want to give a few highlights of Kagome lattice magnet insulators, right? And so here's sort of, I think, the most widely studied one, the so-called Herbert-Smithite. So it's effectively a Kagome net of copper 2+ moments. So this is isotropic spin 1/2 moments, and they're highly frustrated. They are connected via this Kagome network, and this system, down to very low temperatures, doesn't order in any conventional way. In fact, when you look at the excitations out of this this network of copper 2+ or spin 1/2 moments, they're very much consistent with a diffuse spectrum, which are consistent with the creation of pairs of these spin-ons. And so this is just neutron scattering data. So this is showing you energy excitations at various energies, but looking at momentum transfer within the Kagome plane. And so the Brillouin zone here is shown as these hexagons. And basically, the only takeaway here is that the excitations, as they kind of disperse through the zones here, are fractionalized and somewhat consistent with what you would expect for a quantum spin liquid ground state. Okay, another example. This is also from Young Lee's group. This is a Kagome lattice insulator, but in this case, it's a ferromagnet, and this is a strange. This is copper benzene dicarboxylate, and so it's a metal organic system. But the key takeaway here is that you have these copper 2+ moments, but in this case, there's ferromagnetic ground state. And so then the question here is, when I talked about the ferromagnetic insulator, is there indeed experimental evidence that you have this flat band in the magnon spectrum and that it can be gapped from the quadratic band touching? And so indeed, this is work from Young Lee's group where this is a powder average because this is a system that you can only make in powder form in any appreciable quantity. Where again, this is momentum transfer as a function of energy transfer. So this is looking at like a powder average spectrum of the magnon band structure I showed you previously. And so you can see dispersion, and then you see sort of this flattening here. And this is this flat band. And what they do is to further separate the two, they apply a magnetic field out of the plane, and you can see this flat band sort of lifts off. And so this is sort of experimental validation. This is compared with their sort of spin wave calculations, that indeed you can realize these types of states in a real material. Okay. All right, so now so that was a quick overview of just a few highlights of different kinds of interest in Kagome lattice insulators, that's mainly looking at spins in real space. But for Kagome lattice metals, we can go back to this band structure. Okay, so again, we're thinking about like the weak interaction limit. And we can identify sort of three interesting features theoretically that are also been explored more recently experimentally. Okay, so the first is you can think about this Dirac point at the K point. Okay, so this happens at 1/3 filling in the Kagome network. Okay, so that's one region of interest. The second region of interest is you can have a series of two saddle points. Okay, and so these are at 3/12 and 5/12 filling, sort of symmetrically split from the Dirac point. Okay, as we'll talk later in a few slides, that these two saddle points are actually inequivalent. Okay, and that has actually consequences in terms of the types of ground states that one expects to manifest. And then the third kind of area of interest is this flat band filling up here, which is up near 2/3 filling. Okay, and so these are sort of the three regimes. I'm going to step through each of these in the following slides. But okay, maybe I'll stop here. And does anybody have any questions on the insulators or before I start talking about them? Yeah. This?
Yes, this one.
Yeah.
You mentioned here that it has functionalized. Yeah, thank you. So you mentioned here that it has a functionalized spin excitations.
Yeah, that's the model, yeah.
Yeah, so I have questions that do they have functional charge or functional statistics?
They're charge 0, spin 1/2. So the quasi-particle is not a conventional magnon, which would be spin 1. And so basically, instead of creating one magnon, you create a pair of spin-ons that are each spin 1/2.
Ah, okay. Okay, thank you.
Yeah. All right. Any other questions before I move on? All right, good question. All right. Okay, so I'm going to try and talk about some, I delve in a bit deeper to why people are interested in these three features across the Kagome lattice. So the first is just, big picture-wise, what's maybe a reasonable way to visualize the Kagome lattice band structure, at least for me, intuitively. So first of all, the existence of saddle points is not unique, right? I mean, if you look at the sort of Poincaré-Hopf theorem, you have a two-dimensional Brigand zone, I'm guaranteed to have some saddle points, okay? And if I think about the honeycomb band structure here, again, you have this pair of saddle points, you have this Dirac crossing. This is sort of, saw this from Alan's talk to start the day. And this is what you get from this bipartite honeycomb lattice, okay? And as I said at the beginning of the lecture, the original sort of model, the statistical spin physics model for the honeycomb lattice is that you can form, for the Kagome lattice, you can form the Kagome lattice by then just connecting the midpoints of this honeycomb lattice together, okay? And this can form what's called a line. It's called a line graph of the honeycomb lattice. And when you do that, and then you populate the vertices with sites, now I have a 3-site lattice, okay? From this from this mathematical model, basically, if you could connect the two lattices via line graphs, then you're sort of guaranteed to inherit the original bands from the lattice that you created the line graph from, plus you acquire at least a flat band, okay? And so now we have the sort of honeycomb lattice plus this flat band, and we have the Kagome lattice band structure. Okay. All right. So that's one way, sort of intuitively thinking, you know, of where this comes from. For those of you who are more familiar with graphene. Okay. So the first thing to think about is what's the interest at 1/3 filling. So at 1/3 filling, you have this direct crossing at the K point. Okay. And as Alan mentioned at the beginning, you can define sort of a Chern insulator from this by adding spin-orbit coupling into the system, and then you can gap this direct crossing, and you can form what's been modeled as sort of a strong topological insulating state. And in principle, if you could put the Fermi level inside of this gap, then you could realize some quantum spin Hall state. Okay, and so it's another way of saying is that you have protected edge states here. Okay, inside the gap here. So that's one region of interest of the Kagome lattice. A second is you can go up to 2/3 filling, which is this flat band. Okay, this is what Alan was mentioning earlier. Also, you can realize these flat bands in these Moiré systems. And so it turns out that the wave function in this flat band, okay, is what's known as a compact localized state. So you can, for maybe people who are more chemistry oriented, you can think of this akin to sort of a molecular orbital. And the idea is that the wave function sort of alternates in sign across this hexagon. So if you think about hopping, okay, hopping out of this hexagon, you have equal magnitudes of hopping, but with opposite phase, such that they cancel, okay? And so you end up with a state that actually has fixed energy across the Brillouin zone. And so it's an eigenstate of the Kagome lattice Hamiltonian with energy of 2T. Okay, and so this is a way of saying it's quantum interference that's occurring within this state, which localizes it, which makes it a special type of flat band state. I mean, one can think about an insulator, right? I can spread things out, I can get flat bands, but that flat band isn't resulting from quantum interference. And so, so this is actually a result of sort of hopping or kinetic frustration versus magnetic frustration in the system. Okay, and so these are of interest because there's predictions, for instance, that if one can, in this case, if you introduce interactions once you're within this flat band state, in this case, for instance, ferromagnetic interactions, one can generate a quantum anomalous Hall insulator. And in principle, there's been predictions that this can happen at high temperature, which would be useful. But interactions in general within this flat band are non-perturbative, and that means you can get a really rich spectrum of many body states by starting to play around, by populating this flat band state and then allowing tuning different types of interactions within that manifold. And I just want to just pause here and just say, okay, the flat band itself is not necessarily special for a Kagome lattice because you can get flat bands from frustrated hoppings within different lattice architectures as well. Like as I mentioned earlier, this sort of line graph theorem, you're guaranteed to get these type of hopping interference flat bands when you can construct line graphs of different lattice types, right? And so here's some work by Leon Balence's group where again, talking about frustrated hopping models, discussing the Kagome lattice, but also looking at in 3 dimensions. The pyrochlore lattice is another example that should host a 3-dimensional flat band. And for instance, in 2 dimensions, the so-called dice lattice. And so this is a very nice paper that shows that you can basically realize these different lattice models where you can have states that exhibit non-trivial topology due to this flat bands. And the topological structure in real space actually protects the band touchings in the materials. Okay, and there's other examples, so if you're interested, check out this paper. All right. Okay, so then the third region of interest in the Kagome lattice is looking at these regions where you've filled near these saddle points, okay? And again, there's a 3/12 and a 5/12, okay? And so the saddle point, again, looks like this in momentum space, right? You have these sort of crossings of these dispersions with different curvatures, right? And from Van Hove, right? We know that such a saddle point will give you a logarithmic divergence in the density of states. Okay, so the idea then is that you can see that there's not really appreciable changes when you introduce spin-orbit coupling at these sectors of the band structure, but you do have a divergence in the density of states at positions of well-defined momentum. Okay, so in that at the endpoints, and so that means you can get nesting between these endpoints. That can potentially promote electronic instability. And by nesting, what I mean is that you can have, for instance, particle hole excitations or electron excitations between the endpoints along a well-defined wave vector where you have a divergence in the density of states at these points. And so when you look at the sort of Linhart susceptibility, then you can get peaks in the real and imaginary parts of the Linhart susceptibility when you have this strong nesting or this connection at a well-defined wave vector between these points on the Fermi surface. And that can promote instabilities in different forms of electronic order. Okay. And so in a Kagome lattice, what happens when you're near Van Hove fillings, right? When you have this nesting occur? It turns out that you first need to think about there's two different flavors of saddle points, okay? The first, the one at 5/12, is the so-called p-type or pure type. And it's called pure type because when you look at the wave function associated with a given endpoint in the Brillouin zone, in the pure type, that wave function is associated with only orbitals from a single sublattice, okay, that comprises the Kagome network, okay? As I mentioned earlier, it's a 3-sublattice structure, right? If I look at a triangle, I can populate it ABC. So the wave functions here are comprised only from one of those 3 sublattices, okay? And you can see it rotates around as you go around the Brillouin zone to the 3 inequivalent endpoints. Okay, and the lower saddle point is a so-called mixed type, and in that case, you have the wave function is coming from a mixture of 2 of the 3 sublattices. Okay. And so some of the interest in thinking about what can happen if you're near these Van Hove fillings started from some theoretical work. This is from Ronnie Tomale's group, where, again, they're looking at this Kagome lattice Hubbard model, okay, but they're adding an interaction term, an on-site Coulomb interaction term and a nearest neighbor Coulomb interaction term. And the oddity is that when you're in sort of the weak coupling limit, if you're in this sort of pure type or p-type Van Hove singularity, then the on-site Coulomb interaction is either identically 0 or severely diminished depending on the details. Okay, and so they dub this so-called sublattice interference. Okay, and so what that does is it basically promotes the influence of nearest neighbor Coulomb interaction as well as longer range interaction terms. And in some cases, this can result in attractive nearest neighbor site interactions and predictions of unconventional superconductivity. Okay, so this is something that's special to the Kagome network, the pure type Van Hove singularity. Okay, and in fact, you can get very rich theoretical phase diagrams and so depending on how the phase diagram is constructed, you can get a variety of different types of electronic orders that are predicted to form. This is, again, from Ronnie Tomale's group. When you're at this is at this 5/12, so this is at the Van Hove filling. Depending on the strength of the on-site versus nearest neighbor Coulomb interaction term, you can get different magnetic states, different forms of charge bond order, different forms of spin bond order. And then you can see that this phase diagram kind of changes dramatically as you start to just tune the filling a bit, right, with predictions of unconventional superconductivity, in this case F wave. And here's another work, also again looking at the same time, looking at the effect of on-site versus nearest neighbor Coulomb terms when you're at this kind of p-type saddle point in the system, right, with different charge density wave orders, bond orders, etc. So a way to think about it is that the sublattice interference really kind of introduces a lot of complexity and propensity for different kinds of unconventional order into the phase diagrams. And so basically it amplifies the impact of longer range Coulomb terms. Yeah. Can you explain what bond order is? Yeah, okay. So for a charge density wave, you can imagine you can have the charge becomes inhomogeneous and localized on the sites or along the bonds. And so if you can imagine, I can have charge that gets instead localized along the bonds between the sites, and then other things can follow depending on the flavor. Like it can modulate hopping between those sites, for instance, and you can form other kind of more exotic. Okay. All right. Maybe. Okay. It's probably best to ask Alan or somebody like this that if you want the actual rigorous derivation of what it is. But yes, if that puts the charge on the bond, then it's the operator between Ci and Tj. All right. Oh yeah, sure.
Yeah, quick question. So could you comment how realistic or how applicable these calculations are for real systems where you have longer range hoppings? I imagine this somehow messes with this interference, and is this still the effect of this next neighbor interaction? Is this still prominent in real materials, or is it just?
Yeah, that's a great question. So in some cases, so yes, for sure these other interactions are around, and they definitely change, for instance, the band structure, for instance, and renormalize the types of interactions you'll get. And the point of my lecture tomorrow will be to try and now look at real materials, how their band structures look, and what kind of instabilities you can get, and if they can be connected to these models. I would say models which, as I'm going to talk here, that require next nearest neighbor Coulomb interactions are probably not super realistic. But some of the ones with nearest neighbor Coulomb interactions, probably, there seems to be some evidence that that is going on. Yeah. Yeah. So the...
Sorry.
Oh, no, go ahead.
Just a quick question. So are electron-phonon couplings quite relevant in this model with other interactions?
So, okay. What's the relevance of electron-phonon coupling, right?
Yeah. Is it as relevant as the other interactions in this model?
Yes. I think it depends on the material, I think, in terms of the strength of electron-phonon coupling. But I think all of these models are assuming that electron-electron interactions are dominant over electron-phonon. Yeah.
Okay, thank you.
All right. We're good? All right. Okay, just to highlight is another instability that's predicted to occur when you're at this sort of p-type Van Hove filling is a so-called, there's many names for it, so I'm trying to harmonize a little bit. So there's like so-called chiral flux states or something, but they're basically states that are orbital antiferromagnets. Okay, so another way of thinking about it is you can have a charge density wave phase, and if you have an imaginary charge density wave phase, the consequence is you can get these sort of orbital currents that form in your system. And so it's another way of saying it, if we have this like charge bond order that can then acquire this sort of imaginary component, then it can basically modulate hopping around, for instance, one of these hexagons, and you can get these sort of orbital flux phases. So you can imagine it's a system that acquires magnetic order in a magnetic moment, but in the absence of localized moments. Okay? So you imagine you have these little loops, and these loops can have a magnetic moment associated with them, and they propagate in a way such that they cancel out when you look across the unit cell. Okay? So it's an antiferromagnet, but an orbital antiferromagnet. Okay? And there's predictions that one can realize these types of orbital antiferromagnetism. It can either be the primary instability or a secondary instability that's coupled to the real part of the charge density wave order that forms. And there's different patterns that are predicted to form, for instance, across Kagome lattices. And in order to stabilize it, some models require appreciable next nearest neighbor Coulomb interactions. Some require coupled multiple p-wave, p-type Van Hove singularities close to the Fermi level, plus nearest neighbor interactions. But there's different models and different ways to go about getting this to be the ground state on the Kagome lattice. And it's of interest because these types of flux phases map to some of the original predictions, for instance, by Haldane on again, now this is on a honeycomb network where you have now hopping between sublattices of the same type, where you can again generate this type of flux phase, okay? And also, there's other flux phases in different lattice topologies that are predicted. Here's an example by Chandra Varma and the cuprates, for instance, where in this case you have hopping through ligands, not just necessarily between the metal sites themselves. Okay, so this is a copper-oxygen hopping, where you can get, again, a flux phase that sort of cancels out over the unit cell. All right, so this is another instability that people look for in Kagome lattices near Van Hove filling. All right. And so this is maybe like setting up for what I'm going to talk about tomorrow. But the question is then, how would one go about looking for these? So how do you find the right Kagome materials to look for these? Because as was mentioned earlier, some of these effects, there are other effects. There's things like electron-phonon coupling. There's further neighbor exchange. And then for those of us who don't just look in 2 dimensions, we look at 3-dimensional solids, one thinks about the connections in the, this bothersome 3rd dimension when you think about real materials, okay? So when we think about a crystal that we're growing in bulk, you want to try and identify a Kagome network in here, and you want to try and see if that Kagome network, first of all, is relevant for the electronic properties of the Fermi level. And then you also want to see if the assumptions in a Kagome network that is, for instance, quasi-2-dimensional and that is delocalized across the Kagome network, if those hold in the material you're looking at, okay? So effectively, what you want in these real materials is that you want the nearest neighbor distance. That should definitely be the Kagome net bonding, okay, if you can find it. And you want as much as you can, you want weak bonding in the other directions, okay? So this makes it kind of a Kagome approximate. And so if I were to think about this material, and I think about the nearest neighbor bonds, here you have this distance, which I'll call d sub k. You have a well-defined Kagome network. And then you think about what's the next nearest neighbor bonds, sort of out of the Kagome plane. That's in these coordinating antimony atoms in this case. And so you can basically try and think about what's the impact of this sort of non-ideal terms in your crystal structure. So a way of thinking about that is that you want to try and find systems where Kagome networks exist in some type of isolated substructure. And so here's an example for cobalt tin, where again, you think about the nearest neighbor Kagome plane, and you just connect the cobalt atoms via their nearest neighbors, and you get this Kagome plane, and it's sort of reasonably well identified and separated from the next plane, okay? Now, the details about hopping between these planes is a different issue, but at least you can identify the nearest neighbor level that this is a Kagome system. Okay, now here's another system. Now, if I show you this, you'd be like, okay, why are you even showing this, right? But this is a system that has Kagome networks, and it's one of the ones from the C15 Laves phase that I showed at the beginning, right? That's a commonly occurring binary intrametallic. And so this is an example where the Kagome networks are not isolated, right? And so just to kind of maybe drill down a little bit, so here you go. This is basically a network it's a pyrochlore network of metal ions, okay, that I've shown. But if you just say the nearest neighbor bonds, they all connect in equivalent distances in all three dimensions, okay? And so just to highlight, I can look at the 1-1-1 plane in this structure, okay? And then I can remove all the atoms except for the ones along this 1-1-1 plane. And then I can look down the 1-1-1 plane, and then you can see the Kagome network, okay? So basically, you can view it as three intersecting Kagome networks along these 1-1-1 planes, and equivalent planes, that form this pyrochlore lattice, okay? But in this case, the Kagome networks are not isolated, all right? So this is just two extreme limits. Here's one where I have kind of a pure Kagome lattice, and here I'm in the other limit where it's really a three-dimensional structure, okay? So trying to find the materials where you're looking for to try and manifest some of the physics intrinsic to Kagome lattices only, you want to kind of be closer to this limit as much as possible. And so I want to highlight, this is a nice work by Leslie Shoup, where they kind of do a survey of many, maybe not all, I think it's the majority of Kagome compounds in the International Crystallographic Database, or ICSD, and they can categorize them via this so-called tolerance factor, okay? And so the tolerance factor here is they're just looking at the distance between the atoms in the Kagome net, and they're looking at the ratio of that distance over the distance to the nearest atom outside of the Kagome net, okay? And when they do this sort of high throughput, kind of looking at the band structures of these systems, they can kind of ascribe three different regimes, right? Where you can imagine once I move the atoms which are out of the Kagome net to be, substantially closer than those within, then you're not going to get any Kagome bands in the band structure. And then in the other limit, where the Kagome lattice is well isolated from all the neighboring atoms, then you can get clearly Kagome lattice at the Fermi level. This is for the small tolerance factor. And then there's sort of this level in between where the details of the orbitals comprised in the Kagome network really matter, okay, and the orbital overlap in different directions. Okay, so this is quite a nice article exploring maybe, how you can look at an array of materials and try and understand which ones might show Kagome-like band structures and which ones don't when you think about real bonding. And here's, they have a nice periodic table showing, kind of the propensity of different elements to form Kagome nets as you look across the periodic table. And I also want to kind of highlight, because it's relevant for Kagome systems, is there's also a nice survey of flat band materials where, from this topologicalquantumchemistry.com, where you can basically understand sort of ideal flat band systems. Many of these are Kagome-like architectures, okay? And so that's another way of trying to scour these, or you can scour yourself looking at ICSD. And I say this because, a lot of these resources, for instance, I just showed you on the previous paper by Leslie and on this nice quantum materials database, for students now, this is like a unique resource, right? These weren't around 5 or 6 years ago, right? So if you're interested in this type of stuff, there's a lot of resources at hand to try and explore a large array of materials and try and tailor your material to the problem you're interested in. So this is I think it's a real boon for the community. All right, cool. I'm doing it right on time. I'm just going to put my conclusions here. And I just want to emphasize that Kagome lattices, are, to use sort of a military term, like are target-rich materials platforms. So if you're interested in lattices that can host non-trivial electronic topology, but also correlated electron states, then Kagome lattices are a really promising platform to do that. In the insulating regime, they're nearly ideal hosts for highly frustrated magnetic order. In the metallic regime, at various band fillings, you can get different types of behavior, which can host different flavors of unconventional electronic states, ranging from sort of these orbital-only magnetic states to unconventional superconductivity. And I would say most importantly from an experimentalist perspective is that they're not uncommon in nature. So you have a large spectrum of materials to play with and to tune to try and actually approach some of these theoretical predictions and realize them in experiment. With that, I'll thank you very much for your attention.
Thank you, Stephen. Is there any question? Okay.
Thanks for the nice talk. I have a question about possibly exfoliating these to like 2D limit. How feasible is it, and what are the efforts? What are the challenges to like make some gated structure like 2D materials of Kagomes?
Yeah, there are some examples of Kagome systems that are quite exfoliable, but some of them are ionic. So as you get down to the really thin limit, you have to worry about what the charge is and things like this. I think there's a few examples that are exfoliable that I can send you like a reference for or so. But they're typically not van der Waals systems. I think there are some examples, but most of them are ionic. And some are three-dimensional. So a lot of the like purely intermetallic ones that I'll show you tomorrow, they're really not exfoliable. But there's some, for instance, that have alkali metal ions that allow them to be somewhat more chemically 2D and electronically 2D. Yeah.
And with these, are there efforts to like reach this 2D limit? Of, like,
yes. Yeah. People can get them down to maybe like 4 layers or something like that. I think they're getting quite thin. But it gets challenging because, again, some of them are error sensitive, and then some of them you worry about the charge. Yeah.
Nice. Thank you.
So you talked about the localization here being influenced by the quantum interference, which is different from the atomic insulator limit. I don't understand exactly why. So because the states are still localized on the lattice sites. So what makes it fundamentally different from the atomic insulator limit?
I think in the compact localized states, you have hopping, right? With a appreciable magnitude, it's just canceling at the next site, right? Whereas if I were just to spread the atoms out, for instance, to some extreme limit, right, the hopping just kind of exponentially decreases, right? So I think it's due to the interference of the hopping from one side. It's the geometric interference.
Mm-hmm. Okay, thank you.
Yeah. Can you show again the slide with the chiral flux state with the 2 proposals for?
Yeah, there's many more than that, by the way. Yeah. Those are just 2 that I grabbed. Okay, go ahead.
Yeah, that second option with the coupled Van Hove singularities, those are coupled by interactions, or are they 2 different states that can tunnel into each other?
I think they're just 2 different states that are present at the Fermi level, as assumed. So I guess that would mean, I guess it would be tunneling into each other. I don't think they're necessarily coupled via Coulomb interaction or something like this.
Okay. Thank
you. Thanks for the talk. I have a question on the same slide. So these current states, these orbital current states, do they break time reversal symmetry spontaneously?
Yeah.
Okay, but is this why? Because I think for the cuprates, there's also these proposals of orbital current states and that don't break time reversal. So does it have to do something with the sublattice, or what's the reason?
I mean, I think this state breaks time reversal, right, for the cuprates. Are there others that don't? Right, there's sometimes it's funny.
I guess if you have a current anywhere,
Yeah.
you must break time reversal.
But not if it's staggered, right?
I mean, it doesn't break time reversal plus translation then, right? But I think it still breaks time reversal.
Okay.
No more questions. Okay, let's thank Stephen again. He will continue tomorrow with his second lecture.